Hi everyone. Thank you so much for attending my PhD defense. Today I'll be talking about reinventing the protocol stack for next generation mobile networks. So this work has been done under constant guidance of Professor Deepankar Ray Chaudhary, and the committee members include Professor Narayan Mandayam, Professor Predrag Spasojevic, and Professor Carlos from Syracuse University. The key outline of my talk are as follows. At first, I'll be talking about the challenges in the existing protocol stack. Specifically, I'll be focusing on spectrum management issues, mobility management issues, and also transport layer inefficiencies due to millimeter wave intermittency. Next, I'll be talking about our proposed solution to overcome these challenges. And finally, the talk will conclude with a note on future work. There has been an exponential growth in mobile data traffic. So from the Ericsson Mobility Report published in June 2022, we see that global mobile network data traffic is expected to reach 370 hexabyte per month by 2027. Also, various emerging 5G services such as AR, VR, 4K streaming, remote surgery, they all require high bandwidth as well as low latency support. Telecom operators are now focusing on spectrum reuse, dense heterogeneous network deployment, as well as use of millimeter wave bands. But the problem is it introduces new challenges at multiple layers of protocol stack, again due to interoperability and heterogeneity. Okay. So in this slide, we provide some of the challenges and opportunities considering 5G and beyond 5G heterogeneous network deployment as considered in this work. So as you can see here, we have various radio access networks. It may be 5G, LTE, millimeter wave, Wi-Fi, so on and so forth. So in the physical layer, we have challenges associated with spectrum management. In the network layer, we have challenges associated with mobility management due to frequent handoffs. In the transport layer, we have challenges over use of TCP over the wireless channels. So some of the opportunities present within the network include RF devices. It can be made declarative rather than just sensing based. Use of distributed edge cloud resources where we can leverage the compute platform to offload compute intensive tasks involving machine learning as well as certain optimization. Next, in-network support where we can use the feedback from the routers, from the gateways to design efficient and scalable network protocols enabling storage and forwarding. Finally, cross-layer analytics where we take the feedback from the lower layer, let's say from the radio layer, provide it to the upper layers for efficient protocol design as well as the algorithm design. Again, the mapping of the challenges with the opportunities are shown on the slide as considered in this work. The major contribution of this work include to provide better spectrum access, seamless mobility, as well as high-speed data transfer matching MAC limits for next generation networks. So to overcome physical layer challenges, we propose a model-assisted dynamic spectrum access mechanism where specifically we propose spectrum management architecture as well as protocol design. We use standard spectrum model to perform the spectrum assignment. To overcome network layer challenges, we propose distributed mobility management schemes. Specifically, we use cross-layer as well as in-network support to perform efficient handovers. And also we use ideas from name object-based network architecture and associated distributed mobility protocols to perform handovers. To overcome the transport layer challenges, we propose a novel transport protocol for millimeter wave network where there is no probing for available bandwidth, and also our protocol it acts like a base station plugin and it uses cross-layer feedback to perform efficient forwarding. Moving on to next slide. So now I'll be talking about spectrum consumption model assisted dynamic spectrum access. So this work has been done under collaboration with Professor Carlos from Syracuse University, Igor from Columbia University, Dragoslav from Rutgers, Ivan, and also Professor Gill from Columbia University. There has been an increased need for dynamic spectrum access methods for 5G and beyond 5G networks, and this is mainly because of opening up of new unlicensed band, advancement in policies, ongoing standardization efforts, as well as new technologies such as multi-homing or dual connectivity and carrier aggregation. Several centralized and distributed spectrum access methods have been proposed in the past, but the problem with centralized spectrum access method is scalability. You also have single point of failure, and also there exists insufficient local autonomy. The problems in general includes these techniques, these methods, they're not standardized, and because of this, it's often debatable by the parties involved, and also the tools what they have used. Also, the heterogeneity is not accounted for. There also has been a lot of community-driven efforts again towards dynamic spectrum access. For example, DARPA Spectrum Challenge in 2016, Spectrum Innovation Initiative in 2021, and also standardization by IEEE DISPAN community. So considering all this, there is a need for a spectrum management architecture, algorithm design, which use the standard techniques to perform granular DSA in time, frequency, and location. Moving on to next slide. As we have seen before, for the next generation wireless services as well as applications, they'll increasingly rely on dynamic spectrum access methods to enable peaceful coexistence as well as to share the limited spectrum resources. So considering this, we propose a spectrum management architecture, algorithm design, as well as an experimentation framework to be tested on orbit or Cosmos testbed. Specifically, we use SCM. SCM stands for Spectrum Consumption Model, and SIL stands for Collaborative Interaction Language, again developed for DARPA SC2 for spectrum coordination between multiple wireless networks. So coming to the dynamic spectrum management architecture, so it consists of 4 tiers. In the lower tier, we have monitoring and measurement plane, mainly consisting of spectrum sensors to check for spectrum usage as well as accountability of actual spectrum use. On top of that, we have the wireless data plane where we have transmitters and receivers where actual data transmission happens. Now, each of these transmitters, receivers, they're mapped to a wireless domain controller in the wireless domain control plane, and between the wireless domains, we have the SIL protocol to exchange spectrum information. The same SIL protocol is again used to send the optimal transmission parameters to each of these transmitters receivers so that they can adjust their respective parameters. Also, we have a cloud-based spectrum service plane where if we have any complex algorithm involving machine learning or optimization, so we can leverage the cloud infrastructure to run these complex algorithms. Moving on to next slide. So in this slide, I'll be talking about spectrum consumption model. So the data model what we use are called SCMs. SCMs has been standardized by IEEE under 1900.5.2, and it provides various constructs. It's like you have reference power, you have spectrum mask, underlay mask, power map, so on and so forth. So with the help of these constructs, we build transmitter model, receiver model, system model, as well as set model. Also, the standard specifies the compatibility procedure whenever the SCM has been exchanged between multiple devices, just to make sure that those devices will not interfere with each other or not. And that process is called compatibility computation. It's basically the link budget analysis performed between the transmitters and the respective receivers. Moving on to next slide. So in this slide, we provide a timing diagram involving DARPA SIL as well as SCMs. The key assumption what we have here is each wireless domain is only composed of a single transmitter and receiver pair, and they're mapped to a particular wireless domain controller. So at time t1, let's say wireless domain 1, it joins the system, it registers with the regional topology manager, the client table at regional topology manager gets updated, and then you with the help of inform packet, you inform the wireless domain 1 if there are any peers in the system. So since there are no peers in the system, the peer table at wireless domain 1 at time t1 is basically empty. So at time t2, let's say one more wireless domain, it joins the system. Again, you register with the regional topology manager, you update the client table. So now you can see that we have two clients, wireless domain 1 as well as wireless domain 2. Now with the help of inform as well as notify, the regional topology manager will inform the existing wireless domains, and also the respective peer tables gets updated. Now wireless domain 2 will request for the SCM from wireless domain 1. In response, it receives SCM, and then it performs compatibility between the SCMs, and then the report is sent to the respective wireless domains. And also if any change in the transmission parameters are required, we use the configure domain radio APIs to inform the transmitters and receivers so that they can update their parameters. Now also, if any of the wireless domain, if it wants to leave the system, you can send a leave message. The client table gets updated, and also with the help of notify message, even the peer table will be updated. So the ones marked in green are our proposed changes to the SIL, and also we use the protobuf representation of SCMs for efficient transmission between the wireless domains. Next, I'll be talking about dynamic spectrum access using SCMs. So here we propose a spectrum deconfliction algorithm. So the algorithm leverages SIL and SCM for deconfliction, and also it performs dynamic frequency and power adjustment between the transmitters and receivers. And also the algorithm ensures aggregate compatibility with all devices under consideration. So considering the spectrum deconfliction algorithm, we propose two spectrum access methods that use the deconfliction algorithm. Specifically, we propose LCS, logically centralized sequential spectrum access, and then LND, local neighborhood based distributed spectrum access. So coming to the comparison between these two spectrum access methods. So here I have a table representing the differences with respect to the features of the spectrum access methods. So coming to the spectrum assignment, so since it's sequential, we do it in a one by one fashion, but for distributed, you perform parallel assignment. With respect to the required SCMs, for sequential, we take SCMs from all existing devices, whereas for distributed, it's just assigned peers. Coming to the compatibility test, for sequential, we perform compatibility with respect to all devices, whereas for distributed, it's just peer devices. And also in the case of sequential, we have a centralized variable to monitor the interference at each and every receiver, whereas for distributed, it's just locally on a peer-to-peer basis. With respect to algorithm backoff, for sequential, it's based on priority, whereas for distributed, it's based on priority as well as timers. So as an example, priority can be based on the IDs, like it can be min ID, it can be max ID, etc. Coming to the complexity, so since it's sequential, you basically require O of number of nodes for the convergence, whereas for distributed, from our experimental analysis, we found it to be O of chromatic number of a graph. Moving on to next slide. So in this slide, I'll be talking about the spectrum deconfliction algorithms. Uh, so the algorithm leverages SIL and SCMs for spectrum access. So at first you initialize and receive SCMs. Again, based on the spectrum access method, it can be from all existing or just peer devices. And then next, for every new frequency being selected, at first you perform compatibility of new receiver with the existing transmitters. You compute the compatibility score, and then you also obtain the total transmit power at the new receiver. Next, you verify if the score is equal to n minus 1. N is nothing but the total number of link pairs under consideration, again based on the spectrum access methods. You also verify if the total transmit power is less than the allowable power at the new receiver. If yes, we initialize the score to 0. If not, we again see if the total transmit power is greater than the allowable power at the new receiver. If yes, we say that there is an aggregate interference, and then we select a different frequency channel. Next, let's say the score, the new receiver is compatible with the existing transmitters. Now we perform compatibility of new transmitters with the existing receivers. We we again compute the compatibility score as well as the max power margin. We verify if the score is equal to n minus 1. If yes, we say that the link is compatible, we update the interference variable, and then we set up the link. If not, we again verify if the max power margin what we obtain with respect to a set of transmitters, if it's less than the power margin threshold, because we don't want to reduce the power by too much. So here we adjust the total transmit power again based on the max power margin. We again verify if the link is reachable or not. If yes, we update the interference variable, we set up the link. If not, we select a different frequency channel. So as you can see, the algorithm, it leverages SIL and SCMs to perform spectrum assignment, and also we perform dynamically the power adjustment, frequency adjustment, and also we ensure aggregate compatibility with all devices under consideration. Moving on to the next slide. So in this slide, we'll be talking a bit more about the spectrum access methods as described before, specifically LCS and LND. The assumption what we have here is the devices, they show up with default SCM parameters and each having the intent to use spectrum at every time step. The algorithm used is again the spectrum deconfliction algorithm. In the case of LCS, we run the deconfliction algorithm sequentially. Whereas in the case of LND, that is distributed, here each wireless domain is considered as an independent agent performing spectrum assignment on its own. And also we introduce various wireless domain states or status as well as timers and additional messages with respect to the SIL. So coming to the wireless domain status, so we have unassigned and idle, which means spectrum is not assigned. We also have pre-assignment, which means wireless domain needs to perform spectrum assignment. We have a pause state, which means we temporarily pause pre-assignment. We have running, which means wireless domain is running the deconfliction algorithm, and assigned, which means the wireless domain has completed the spectrum assignment. We also have timers again to prevent infinite wait in the pre-assignment pause as well as running state. In addition to the SIL messages, the following messages are also required, like node status request and response, the acknowledgement message, the assigned message, as well as the reset message. We also need an interference graph, which is again obtained during the bootstrapping phase by the exchange of beacons between the immediate one hop peers. Next, we describe in detail our proposed distributed spectrum access method. So let's consider a simple topology consisting of three nodes. So here wireless domain 1, it has two peers, wireless domain 2 as well as wireless domain 3. When looking at the timing diagram, so let's say wireless domain 1 is interested in performing spectrum assignment. It enters the pre-assignment state, whereas wireless domain 2 and wireless domain 3, it's currently in unassigned state. So at first, wireless domain 1, it sends the NSR, the peers, they receive NSR, they immediately turn to pause state, and in response, the peers, they send back the NSRP, the response packet with the unassigned state. Now wireless domain 1, it has received NSRPs or the response from all the peers. It enters the running state where it performs the deconfliction algorithms, or it runs the deconfliction algorithms. And in the meantime, the wireless domain 1, it also sends an acknowledgement to the wireless domain 2 as well as wireless domain 3, informing that it will be the next to perform spectrum assignment. So once the spectrum has been assigned, wireless domain 1, it enters the assigned state, and then the assigned message is sent to wireless domain 2 as well as wireless domain 3. So as soon as the assigned message has been received by the peers, they can enter the pre-assignment state if they want to perform spectrum assignment, or they can remain unassigned. Also, please note that we have various timers like NSR timer, acknowledgement timers, as well as restart timer, again to prevent the infinite wait or infinite loop in the respective states. Also, if there is any conflict between the peers in performing the spectrum assignment, In our current implementation, we resolve this conflict based on IDs. So lower IDs are they are given high priority as compared to the other nodes. Okay, so if we evaluate our proposed access methods considering a Python simulation, but specifically for distributed spectrum access, we use Mesa, a Python agent-based modeling tool. So here it consists of two classes, the model class as well as the agent class. So in the model class, at first we have model level parameters and variables, for example, the number of agents. We also have a deployment or the mobility model, mainly consisting of like where we want to deploy these transmitters and receivers, and also if there are any associated mobility trajectory, so even that can be specified in this module. Next, we also have the scheduler module, where we decide how we want to activate the particular agent. It may be simultaneous activation, it may be random activation, sequential, so on and so forth. So in our implementation, we use simultaneous activation. We also have a step module where we advance the simulation. Coming to the agent class, at first we again have the agent level parameters as well as variables. It may be the node or wireless domain status. We also have a step module where we stage any necessary changes, and then we also have an advanced module where we apply those particular staged changes. So moving on to next slide. So in this slide, I'll be talking about the SCM generation as well as simulation setup. So here the SCMs what we use in our analysis, they're again obtained from Orbit USRPs with the following experimentation setup. So here we consider a BPSK modulated signal with the bit rate of 0.5 megabits per second and bandwidth 1 megahertz, central frequency at 2 gigahertz. We use USRP's X310 as well as B210s. So here on the left I have receiver underlay mask, whereas on the right I have transmitter spectrum mask. Okay, so the transmitter spectrum mask, it represents how the RF energy is radiated as well as propagated with respect to a particular transmitter. In the case of receiver underlay mask, it represents the incompatible interference for that particular receiver, and also the sensitivity of the receiver is being represented in the receiver underlay mask. So the SCMs generated were again used to evaluate large-scale SCM-enabled dynamic spectrum access considering Python simulation. These are all the simulation parameters what we have. We have an operational area set to zero point 0.5 square mile, and then we uniformly deploy these transmitters and receivers with a certain minimum transmitter separation distance as well as transmitter receiver separation distance. We have set the power margin threshold to 3 dB, and also in our evaluation we perform or we evaluate with respect to large number of trials like 100 in our case. Okay. So coming to the performance evaluation, so at first we evaluate the convergence of our spectrum access method. Uh, so on the left, I have a plot of assigned wireless domain versus the time step. Again, considering distributed spectrum access. So here I have performed an experiment with respect to single trial, and then I have 100 links or wireless domain in total. So as you can see that with distributed spectrum access, considering p equal to 200 meters, we require 13 steps to perform assignments for all the 100 links. We also observe that with the increase in p, the more time is required to perform the assignment or the convergence. On the right, I have a plot of step count versus a different link configuration. It may be 10, 20, 50, and even 100. So here we see that for sequential, like since you're performing it in a one by one fashion, we require around, we require 100 steps for 100 links. Whereas for distributed, considering average value over 100 trials, we require around 13.76 steps to perform the deconfliction. We also see that the convergence of distributed is found to be similar to the chromatic number of a graph. Uh, Again, we evaluate this particular value from the graph coloring algorithms obtained from the Python Network X package. So here we see that considering random graph coloring or desaturation, breadth first search or depth first search, we see that our value is close to the chromatic number of a graph. Again, considering 100 trials as well as p equal to 200. Okay, so coming to the spectrum usage, so here on the left, I have a spectrum usage for sequential spectrum axis. On the right, I have spectrum usage for distributed spectrum axis. Again, for different link configuration like 10, 50, and 100. So here we see that the channel usage of sequential and distributed axis with p equal to 200 meters is found to be similar. 400 links, the maximum number of channel required is 17, whereas the mode number of channel required for 100 link is found to be 13. We also have one more metric called global compatibility error, where we compute this metric after you perform assignment, and in the case of distributed, just to ensure that we are compatible with the existing system. So here, considering p equal to 100 meters, the error is found to be 22.9% for 100 links, whereas with p equal to 1 meters, the error is found to be 0, which again means that up to 200 meters you observe interference from the neighboring peers, and that's well captured with the SCMs. But if you just use, or if you're just restricted to peer equal to 100 meters, you have a very high error of 22.9%. Again, to be precise, it's basically the hidden node issue what we observe here. Okay. Moving on to next slide. So here we compare our algorithm with the baseline version, where we just perform the frequency adjustment. There is no power adjustment in the case of baseline. So here I have a channel usage considering baseline as well as the sequential algorithm, and for 100 links and for 100 trials. Also here I've considered two variants of sequential spectrum axis, the no power margin threshold as well as 3 dB power margin threshold. So in the case of no power margin, like there is no threshold, and we limit the power to the ideal or optimal setting. So here this scheme basically represents the maximum potential gain that can be achieved with our proposed algorithm. Whereas for baseline, since there is no power adjustment, it uses large number of channels at full power, and that's again observed from the channel usage, because baseline requires around 14 channels, whereas sequential no power margin you require 12 channels considering mode channel usage. Okay, so on the right, I have a plot of a computation time versus the number of link pairs in the system. And here, the computation time does not include the pauses between the new link pair instances, the time to turn on RF devices, and also SCM transmission time, which is again few milliseconds. So we see that with sequential, like since we are performing compatibility with all existing devices, a very high computation time is observed per link, which is 3.25 seconds. But for distributed, since you are just performing compatibility only with respect to the peers, it's just zero point 0.17 seconds per link. And also this is because we have less number of compatibility tests, unlike sequential where we have large number of compatibility tests to be performed. Okay. We also have a proof of concept orbit and or Cosmos testbed implementation. So here again we just consider frequency adjustments because of the limitation with the hardware devices. So at first we have a ZMQ server which acts like a regional topology manager. So at time t1, wireless domain 1 with transmitter and receiver, it shows up, it registers with the ZMQ server, and then here, so since there are no devices in the system, it's free to use its own or existing transmission parameters. So then it sets up the link, and then that can again be observed in the power spectral density plot as well as the waterfall plot. At time t2, wireless domain 2 shows up. you register with the ZMQ server, and then you exchange SCMs. You perform compatibility, and then it decides that it cannot use the same set of parameters as WD1. So it ended up selecting a different channel or a different frequency, which is away from wireless domain 1. At time T3, wireless domain 3 shows up, you register with ZMQ server, and then here you receive SCMs from both wireless domain 1 as well as wireless domain 2. You perform compatibility, and then you again select a different frequency, which is again away from these two frequencies. So please note that so here we are using orbit testbed. So all these three links will interfere with each other if they operate on same channel. So that's why in the end it ended up selecting a three unique or a different channel. And also the node mapping as well as USRPs are again shown on the slide as considered in our implementation. Finally, I also have a demo video showing how our protocol works in real time. So at first, as you can see here, we have various handshake messages with respect to ZMQ server, again with respect to peers. Then you receive SCMs, you perform compatibility. So here we have 4 tests because already 2 links or 2 wireless domains are active. So the new receiver with existing transmitters, new transmitters with existing receivers. It ended up selecting a different frequency, which is 2001 in our case, and then you start the transmitters and receivers. So here we see that the power spectral density plot is slightly different from the other two because we are using a different device, which is B210 as compared to X310, and a slight out of band interference is observed, which can again be easily modeled with the help of SCMs. And also you can see that the packets are being received at the receiver window.
This completes my topic on spectrum assignment. Next, I'll be talking about network-assisted distributed mobility management. This work has been done under collaboration with Sumit Maheshwari from Rutgers University. Okay, so moving on to next slide. Considering dense heterogeneous deployment of cells as well as heterogeneous user requirement, we have a lot of network challenges. It may be challenges with frequent handoffs. It may be with the load balancing, providing seamless access. So mobile handoff, it decreases user quality of service. You reset the TCP connection every time with the handover. And also this again increases the control plane messages. Also, there is lack of coordination between the components of the network, let's say the base station, the intermediate routers, and this again causes the change in IP address every time during the handover, again if managed by different entities, which again leads to suboptimal routing as well as potential bottleneck at the gateways. So considering all this, there is a need for a scalable and distributed mobility management schemes enabling seamless connectivity among the heterogeneous networks. Okay, next we provide a qualitative comparison of different mobility management schemes currently under consideration. So considering mobile IP, so here we have a partially distributed host-based seamless IP access scheme. So here addressing is based on home address and care of address, and also we use IP tunnels again to send the packets from the previous access points to the new access point, and there are multiple mobility anchors. So since you're using IP tunnels, you have high signaling overhead, which again leads to low route. There's no route optimization. Considering proxy mobile IP, so here you follow a similar architecture to the mobile IP, but the management is performed by the network rather than host in the case of mobile IP. Considering SDN, so here you have a centralized architecture. So here management is performed by the network. It can also be the centralized controller, and then we have fixed IPs or IDs. Also, we have multiple mobility anchors, or even the central a single mobility anchor. There is no tunneling as such and because of that, you have very high route optimization with medium signaling overhead. Considering name-based network architecture, which in our case we use mobility first, so here it's a fully distributed architecture. The management is performed by the network, and we use fixed IDs. Like here we use GUIDs for addressing, and there is no mobility anchor as such, and also no tunneling, so which again leads to very low signaling overhead and high route optimization. Okay, next we provide a brief overview of the mobility first architecture and also various components being used. So mobility first is built upon a name-based service layer, which acts like a narrow waist of the protocol stack. So here you have a clean separation between the GUIDs and then the network address. So these GUIDs are not just given to devices, but they're also given to context, and they remain fixed throughout the lifetime of a device. Also, we have GNRS mainly to resolve GUIDs with the network address. The routing is again based on storage aware and DTN mechanism, where we use short-term and long-term expected transmission time, basically to forward the packet. And then the transport is based on hop-by-hop protocol, where you reliably transport the large block of data rather than small chunks. And we have the bitmap of the packet being used basically to identify any loss. So more details on the mobility first can again be obtained in the website below. Okay. Next, I'll be talking about our proposed handoff scheme, again considering mobility first architecture. So here we propose two handover mechanism, hard handoff with rebinding, and then soft handoff with multihoming. So considering hard handoff with rebinding, so here the undelivered packet due to poor channel quality, again during handover, they're basically buffered at the previous access point, which in our case AP1, and then they're rebound to the new UV location, which in our case is again AP2, when the UV attaches to the network. Coming to the timing diagram, so here UV initially attaches to the AP1, you insert an entry into the GNRS, you again update like X is mapped to AP1, a data flow path is set up. Now, if there is any decrease in channel quality, the UV attaches to AP2, you update the entry, so X is mapped to AP2. Now, the previous base station or access point, it requests from the GNRS the current UV location, which in our case is AP2. So based on that, the packets stored, they're basically sent to AP2, and then later they're forwarded to the user. So this calls for a zero packet loss handover, and also the UV is not aware of packet rerouting except listening to the new channel. Here we can have two schemes, pull and push. So pull is initiated by the access point, whereas the push is initiated by the GNRS whenever the user attaches to the new network. Moving on to soft handoff with multi-homing. So here we use both the interfaces, so it can be Wi-Fi, LTE, or anything. Like you can use both the interfaces simultaneously during the routing. If you look at the timing diagram, here UV initially attaches to AP1, you insert an entry into the GNRS, a data flow path is set up. If there is any decrease in channel quality, the UV attaches to AP2, you again insert an entry. So X is mapped to AP1 as well as AP2. So you can continue using both the interfaces, but if any of the interface, if it has poor channel quality, you can basically disassociate that particular interface. So this calls for a make before break handoff mechanism. So here UV is multi-home and it can keep using both the interfaces. So this again calls for improved user quality of service as well as throughput. We can integrate the proposed handoff scheme with the existing IP network with the help of overlay mechanism. So here we can have a naming layer over IP or UDP for incremental deployment. We evaluate our proposed handoff scheme considering the click implementation of mobility first. The system diagram consists of file server, the UV stack, GNRS, as well as MF capable routers, and then the access points. So here we use MF ping and then MF perf a modified version of ping and perf in our evaluation. So here I have two plots for hard handoff. On the left, I have the RTT plot. On the right, I have the throughput plot. So here we see that the handoff has occurred at packet sequence 20, and during the handover, the three packets are basically buffered and then they're rebound after 3.21 seconds. The additional 200 milliseconds is mainly because of the routing as well as synchronization issues. So coming to the throughput plot, here we observe a peak right after the handoff, and that's mainly because of the rebinding what we have. So rebinding, it prevents end-to-end retransmission and then it minimizes the latency. So coming to the evaluation with respect to soft handoff, so at first I have a homogeneous Wi-Fi network. So here again the handover has occurred at packet sequence 20, where after 20 you use both the interfaces. Now the bifurcation router can decide which interface to choose, again based on the data rate. So here we can see that after 20, like you have certain peaks with higher RTT, let's say 20 or maybe 28 milliseconds. That's mainly because it's using the old interface with the poor channel quality. So you can basically disassociate that interface, or you can again continue using the interface. Next, I have a heterogeneous setup where I have a Wi-Fi as well as LTE network. So here we have integrated mobility first with the open air we have integrated mobility first with the LTE network using open air interface L2 tunnels. So here we see that the soft handoff, it performs better as compared to hard handoff. Again, the RTT is bounded, so that's why it performs better. Okay. We also evaluated our proposed handover schemes considering a dense heterogeneous deployment where we have a macro cell as well as multiple small cells using MATLAB simulation. Here we have a flat core architecture with no hierarchy to reach internet, again for both small as well as the macro cell. So in our simulation, we have a single macro cell with a radius of 500 meters and then 60 small cells with a radius of 50 meters. The user trajectory is again obtained from the CrawDad website. These are all the simulation parameters what we have in our simulation. So coming to the UV axis schemes, so here we have macro only scheme. We have the best available interface scheme where we decide which interface to select, again based on the throughput. We also have multi-homing with rebinding where we use both the interfaces when available, and also any packet lost during the handover, they are rebound to new network addresses. Coming to the scheduling schemes, so here we have a macro only scheme. We have round robin for both uplink and downlink. Round robin for downlink, best interface for uplink, again round robin for uplink, best interface for downlink, and then best interface for uplink as well as downlink. So to emulate handover, we have considered handoff latency as 65 milliseconds between macro and small cell, and 300 milliseconds between the small cells to emulate the handovers. So coming to the evaluation results, so on the left I have a throughput plot versus entire user trajectory. So here we see that if you just use macro cell, the throughput is roughly around 5 megabits per second. But if you use both the interface like multi-homing based soft handoff, we observe a throughput gain of 12.5% for mobile user and then 16% for static user. Also during the entire user trajectory, around 12,000 packets, roughly of size 1000 bytes, they are buffered at the previous access point and then they're rebound to the new network address during the entire user trajectory.
Can you go back a few slides just to see the topology?
Okay.
This one. So you simulated this Microsoft small cells.
Yeah. So I have one macro cell and then 60 small cells, and then these are my user trajectories. And also I'm considering 10 trials. The user trajectory will remain the same, but the deployment of the base stations, they will vary.
Basically, each time, sort of like each dot here is a transmission to the microcell small.
Yes, yes. Like we have used log distance propagation loss model Yeah, these are all the simulation parameters. Like macro, we have bandwidth of 5 megahertz, small it's 20, and these are all the TX parts.
And the blue dots are like they should be somehow connected because that's your trajectory.
Yeah, this is my user trajectory.
Okay, but you somehow like fork. Some of them look like forking.
Yeah, because the start and end is actually the same.
Oh, you come back. Okay.
Yeah, you come back. Yeah.
Okay. It's only one transmission at a time. There's no interference.
No, nothing. Yeah. Just to evaluate the performance with the handoff schemes, which you can get.
Yeah, sure. Trying to get a picture.
Oh, okay. Okay. So coming to the throughput plot. Sorry, I think I finished the throughput plot. Okay. With respect to the round trip time, so here if you just use macro cell, you have a RTT of 35 milliseconds. Yeah, but before that, we have developed a ping-lag application with the packet size of 1000 bytes, again, to evaluate the round trip time. So we see that round robin, it performs poorly among other schemes being considered. And we also observe that round robin for downlink and best interface for uplink, it provides a comparable performance with best interface for both uplink and downlink. So this is mainly because of the uplink channel access time, which is roughly around 17 milliseconds for the macro cell. So again, based on the application requirement, user requirement, so here we are free to select any scheduling scheme at the intermediate router as well as at the UV to perform the data transmission, again, during the handovers. Yeah, this concludes my topic, my talk on the network-assisted handoffs. Yeah, so now I'll be talking about cross-layer transfer protocol for 5G millimeter wave network. So this work has been done under collaboration with Jiacheng Chen from Rutgers University. Okay, so as we all know, millimeter wave, since it has a vast bandwidth, it can provide a gigabit per second throughput. But there exists a lot of challenges with respect to the physical layer characteristics. Millimeter wave links, they're highly susceptible to blockages. So it may be with the buildings or human body. And also you have rapid fluctuations between the signal's strength. It may be with the line of sight as well as non-line of sight paths. And you also have certain level of attenuation. It may be with the oxygen as well as rain absorption. So this has a direct impact on the upper layers. So it causes poor transport performance, again, if you use TCP for now. So here with the TCP, like you have frequent timeouts, again, because of the blockages, and also it causes slow growth in congestion window. This often confuses the application logic, let's say bit rate adaptation, like for example, YouTube, like it uses the bit rate adaptation algorithm to perform the data transmission. To motivate further, we again perform an experiment on orbit testbed. So here we have a topology consisting of server, base station, and then the UV. We again obtain the millimeter wave mobility model from the paper cited below, where the authors, they have conducted an experiment in Minneapolis downtown area with the real 5G capable phone and then Verizon 5G network. So in our case, we emulate the millimeter wave using Ethernet channel, and we have the 4G throughput set to 20 megabit per second, and then the 5G throughput again set to 1 gigabit per second, and we have the round trip time as set to 50 milliseconds. So here we see that there is a frequent handoff between 4G and 5G, and let's say if you use TCP, so it takes considerable amount of time to reach the optimal millimeter wave capacity. So let's say at time stamp 30, like it takes around 20 to 30 seconds to reach optimal 1 gigabit per second. And also sometimes it's not even possible to reach the optimal millimeter wave capacity. So the main issue or the main TCP principle behind this issue is TCP works on probing mechanism, like you probe for the available bandwidth, and also you use the same mechanism to detect packet loss as well as congestion control. So it works on an end-to-end basis. So this calls for a new transfer protocol, again, to overcome the limitation of TCP, again, to avoid probing and also wastage of bandwidth during the millimeter wave outages. Next, we again perform more experiments and then we evaluate the TCP.
Can you say a few words on the mobility model?
Yeah, the mobility model was again obtained from the paper cited.
Right, but what does it say?
So here the user is actually walking in a downtown area, Minneapolis, with the 5G Galaxy phone, and you have both the interfaces. Like you have 4G support as well as the mmWave support, and it's actually an 8-minute walk in the area. And the Verizon, they have deployed mmWave base station in that area, and they're running. I mean, here I'm just getting the timestamp of the handoffs.
Okay.
And then we emulate the mmWave using Ethernet channel.
Okay.
But in their paper, they have provided the throughput values what they obtain with the network.
And this sort of lag, how do they model the lag? Or
No, it's observed in their case.
Observed.
But here I want to quantify what that lag is. So that's why I performed an experiment using the Ethernet channel.
On Ethernet, you won't see the TCP.
Yeah. TCP cubic. TCP cubic.
No. So you have channel impairments here, which put the 4G and 5G.
Just 4G and 5G handoffs. So 4G throughput is set to 20 megabit per second, and then the 5G throughput is set to 1 gigabit per second. So just to see the time it takes from low bandwidth, I mean from low rate to the high data rate.
TCP is slow start.
Exactly, slow start. Yeah.
Just because TCP is not aware that you have a...
Exactly.
How you get those?
Yeah. Like I have more results as well.
No, it's fine. Just trying to understand what is from the model they provide
Right.
that you use.
Yeah.
Okay.
Okay. Yeah, so here in our next experiment, we again validate the TCP performance over mmWave network. So to begin with, we consider a point-to-point link with the interdigital 60 gigahertz device, again available as a part of Cosmos testbed. So here we set the TXRX distance to be 25 feet, the blockage interval roughly around 5 seconds. So here we see that during blockage, the throughput drops to 0, and whenever the user moves away, again the throughput again shoots back. Also, we see that with the slight shift in the TX orientation, let's say with the 10 degree or maybe 30 degree, the throughput drops drastically. So next, we also perform another experiment where we actually compute the recovery time from non-line of sight to the line of sight. Again, from 20 megabit per second to 1 gigabit per second. So here I have a plot of time versus throughput for different values of RTT. So let's say you have a very high RTT of 100 milliseconds. The time, the recovery time can be as high as 33 seconds. Yeah. So mmWave links, they're again highly susceptible to blockages. So higher the RTT, more time it takes to reach the optimal mmWave capacity. So considering all this, like we propose a novel protocol, like it's called as mmCPTP, a cross-layer pull-based transport protocol. The key design objectives as well as design concepts of our protocol is again will be described next. At first, with respect to the design objectives, support mmWave intermittency and capacity. As we have seen before, the TCP probing, it takes a lot of time to reach the optimal mmWave capacity. Again, we have frequent fluctuations between 4G and 5G. So the protocol should be capable of reaching the optimal optimal link capacity as soon as possible or as early as possible. Next, support seamless mobility. Also, we have seen before, the TCP resets the connection every time with the handover, again, if there is any change in IP address. So there is a need for in-network routing as well as rebinding of data packets. Next, congestion control and then packet loss. So TCP, it considers the same mechanism to identify congestion control as well as the packet loss. This again decreases the quality of service. So we need a better mechanism to handle this. So coming to the design concepts of our protocol. So here to support mmWave intermittency and capacity, we propose a protocol, a novel pull mechanism where there is no probing, like we totally avoid probing. We know that the base station is basically the last hop is the bottleneck, the link from base station to the user. So here we pull the packet from the file server or proxy present closer to the packet, closer to the user, based on lower layer RLC or MAC buffer information. Next, to support seamless mobility, we propose a split connection where we break the link into wired as well as wireless part with the help of a proxy. The sender is unaware of any ongoing interruption, and it's free to send the data with the applicable rate to the proxy. Next, we also propose a separate mechanism to handle congestion control and then the packet loss. The packet loss is taken care by the lower layers of stack, such as link or the MAC, and then the flow and congestion control only taken care by the transport layer. So this again prevents any adverse impact on the higher layers. Okay. So coming to the protocol design details, so on the left I have a high-level architecture of mmCP/TP. So here you can see that we use pull mechanism to retrieve the data packet from the proxy present closer to the user. So if your data is not present at the proxy, traditional mechanism can be used to retrieve the data packet from the remote file server. It can be even any other AIMD mechanisms. Also, we know that the bottleneck is basically the last hop, so our protocol sits on top of the bottleneck link. The goal here is to eliminate and allow fast fluctuation between line of sight and non-line of sight path. Coming to the key details, so here we have pull-based flow and congestion control, again subjected to the buffer occupancy, pull buffer at present at the base station, and we have various pull techniques like periodic pull or even the threshold-based pull, again based on the buffer size. We have AIMD-based flow control, again between the file server and the proxy to again retrieve the data to the proxy. Also, coming to the error recovery, we have selective acknowledgement, we have acknowledgement as well as negative acknowledgement to recover any lost packet between the components of our protocol. And also, as you have seen before, our protocol, it's a cross-layer base station plugin. So the design involves layer 2 and layer 4. So it can easily work on any layer 3 option. It may be IP, 3GPP, NDN, or even the mobility first. Yeah. So here the proxy is actually present at an infrastructure end. It may be an edge cloud, so hence it expects less failure, and also various other lower layer error recovery techniques such as HARC can also be used to aid packet delivery. Okay, so coming to the timing diagram, so here I have a content server, proxy, base station, and then the UV. So at first the UV resolves for the content addressed to the nearby proxy, and then the UV request for the proxy request for the content from the proxy. So if the data is present at the proxy, it can be retrieved using pull. If not, an HTTP request is sent all the way to the content server, and then you set up a TCP session between the content server and then the proxy, and then you get the data. So as the data arrives at the proxy, a single data packet is sent to the base station. A pull buffer is initialized at the base station on a per UV basis, and then a pull packet is sent again to fill in the pull buffer. So as the proxy receives the pull message, a counter is initialized, and then those many data packets are again sent to the user. If there is any loss, we can use selective acknowledgement mechanism to recover the loss. And also in this particular use case, like we have used periodic pull, where every T millisecond we pull the packet from the proxy based on the buffer occupancy. Next, the data transmission, again based on MAC layer scheduling, you can send the base station sends or schedules the data to the user. And also we have an acknowledgement from the UV to the base station, which is again discarded by the base station. Okay.
You're not showing TCP from the UV?
There is no, because our protocol, like we have a protocol which uses pull. So there is no.
It stops at the TCP stops at the proxy.
At the proxy.
So you're not splitting TCP. You're terminating it.
Yeah, terminating it.
question was, how big a buffer would you need? Basically, what you're doing is just inserting a layer to prevent multiplicative decrease. Right?
Yeah.
So how long would you?
It again depends on the data rate. Let's say if your millimeter wave, it can support gigabit per second. So based on the BDP product, the bandwidth and then the latency product, so that much of size, it can be in several megabytes. It can be tens of megabytes. So that much of buffer on per UV basis, it has to be initialized at the base station.
Yeah, so I mean, yeah.
So basically, whatever is the bandwidth gain that you want to use with the mmWave,
Yeah.
you need that amount of storage, right?
Yes, yes. Also with the millimeter wave, the problem is like you have a very short-term interruption. It may be with your hand, like if you place your hand against the antenna, so again there is an interruption. So with the buffer, like whenever the channel shows up, like you can send the data packets to the user.
I guess my question is, it could get costly really quickly, right? At the buffer end. You're assuming that
No, but this buffer is present closer to the user. So you can also you can actually send the data, like let's say you have a handover to a new base station. You can basically reroute the data to the new base station. So there is no end-to-end retransmission as such present in the TCP.
That session can be maintained indefinitely.
Exactly.
What's on the UE? What's the application? What is it using?
I mean, in my evaluation, it's just I'm using iPerf, like content retrieval. Like I'm basically retrieving large amount of data from the remote file server.
It's a standard UE. You have Android. It's running an application. Expect to send out.
Yeah, but coming to the application, it can be 4K streaming, where you require very high bandwidth again to stream the data. It can also be the Google Cloud kind of update, like where you want to sync your phone to the cloud. So that again requires very large bandwidth. And also the VR headsets, all those.
So some specialized application where the UE, specialized application that the UE is aware of.
No, in this case, it's just a content retrieval. So here I'm retrieving a very large amount of data from the remote file server. So that application I'm basically considering. Again, it can be mapped to the 4K streaming. It can also be mapped to the sync between Google Cloud and your phone, where you require very large bandwidth. So we can think in those terms as well. Okay. So coming to the implementation detail, so at first we propose a pull-based abstract layer, again as shown on the slide. The main purpose of this abstract layer is no matter what your underlying L2 protocol is, it may be Wi-Fi, it may be LTE, it may be NR. So our transfer protocol, it can work with any of these schemes. We also provide various socket interfaces like send, pull, receive packets, report buffer status, so on and so forth. So as an example, we integrate our protocol with the 5G NR stack. We leverage most part of the code from NS3 LTE module because NR will be using the same RRC, PDCP as well as RLC layer, but different MAC and PHY layer. So our solution, it sits on top of the PDCP layer. And also in the case of NR, we are getting feedback from the RLC buffer or RLC buffer status. Again, to get the feedback from the RLC, we require information on the tunnel endpoint identifier, RNTI, RBID, etc. And again, these information, they're again packaged, again sent to the abstract layer, and with the help of that, you can retrieve the information on the RLC buffer status. Yeah, so again, the figure is again shown on the slide. Okay, so moving on to next slide, we evaluate our proposed protocol considering urban macro cell deployment. So here I have a single millimeter wave base station and then a UV in a downtown area. So here I have considered various mobility models. Let's say user is moving along x-axis, user is also moving along y-axis, and also the black ones, like what you can see here, they're basically the buildings, like mainly to model buildings. So coming to the random walk trace, an example SINR trace is again provided. So here we see that under blockage, the SINR can be as low as -40 dB, but with the line of sight path, the SINR can be as high as 20 dB. So these are all our simulation parameters, which, I mean, we are using NS3 in our case. So with respect to the NR stack evaluation, the underlying channel being considered is LTE, which is again centered at 2 gigahertz. And these are all the resource blocks, 25, 50, and then 100. But for trace-driven emulation with the help of Ethernet channel, we are using a millimeter wave trace, which is again centered at 28 gigs with 1 gigahertz of bandwidth. And these traces were again obtained from NYU millimeter wave sim. Okay, so moving on to next slide. So here I have.
This is your track. Is there millimeter wave over the air, or is it
like I have two evaluations, like NR stack and then trace driven evaluation. So for NR stack, it's the LTE channel. But for trace driven emulation, it's the millimeter wave channel.
LTE channel is at 2 gigahertz?
Yeah, 2 gigahertz. Because LTE module, I was using NS3 LTE modules. Okay. So coming to the evaluation with respect to single user. So here I have this particular topology: file server, EPC, base station, and then the UV. Roughly the round trip time is around 25 milliseconds. So let's say we have this particular trace. Again, it's again obtained from the lower layers. So here UV is moving along x-axis. So here we see that our protocol, it outperforms TCP neuron node, TCP cubic, and also the throughput is very close to the MAC layer throughput. So a gain of 2.5x and 1.3x is observed with neuron node and cubic respectively. Also, the gain increases with the increase in resource block size, because more the bandwidth, the more the gain is observed, because our protocol is again meant to optimize these short-term outages. We also evaluated with respect to emulated UV outage model, where we kind of inject outage for a time uniformly distributed between 0.1 to 2 seconds. So here we have a higher gain is observed because our protocol is again meant to optimize these temporary outages, hence a higher gain is basically observed. So coming to the next slide, so here we evaluate with respect to two users, like multiple users. Again, the RDT is roughly 25 milliseconds. So here user 1 is basically stationary. It remains in line of sight path throughout the simulation. UV2 is mobile, where I'm using an emulated mobility model as shown before. Okay, so we see that with our protocol, a max throughput gain of 2.8x and 1.5x is observed with neuron node and cubic for mobile user. An interesting thing here is the performance deteriorates for stationary user because it's mainly because of the PF scheduler at the base station, because now your share for mobile user has increased, which again means that like your share for the stationary or the line of sight path, which was using lot of resource blocks before, so that has to be reduced mainly because of the scheduler. We again quantify this particular value here, like how much of fairness is imposed by our protocol as compared to neuron node and cubic. We use Jane's fairness index. It's given by this particular equation. So here we consider Xi as application throughput proportional to the MAC layer throughput, and we see that our value is basically closer to the 1, and JFI equal to 1 represents highest fairness index. So our protocol, it provides better fairness index because it sits right on top of the bottleneck link, and it operates closely with the MAC scheduler as well as lower layer buffer information. Okay, moving on to next slide.
So, just one question.
Yeah.
When you do throughput, right, it's an average value, but I suspect that there's more variation. Mm-hmm. Did you measure that?
Like in my case, like it's just one trial, and the user is moving from like basically along x-axis where you have buildings in between, and the simulation duration is roughly around 1 minute or something.
When you're blocked.
But I have a fixed deployment area, right? So no matter how much ever times I run, I'm gonna get the same channel because it's a simulation.
But like if you're in a dump, you won't get that. So the variance.
Yeah, that's true. But I think the LTE because I'm using NR stacks, that's basically considered here. I think they have a model, underlying model which does that, but I'm not capturing it here. Okay, so coming to the end-to-end evaluation. So here we use mmWave trace again obtained from the NYU SIM. So we have the following topology. We have the file server, proxy, router, and then the base station. We evaluate our protocol with TCP and then ITCP. So when I say ITCP, like you have two separate TCP sessions, one from file server to proxy, and then the other one from proxy to the user. So we see that considering random walk, with our protocol, we are quickly able to recover from these outages. A gain of 31% is observed with our scheme as compared to ITCP cubic. And also the performance with TCP is so poorly that, it performs so poor that after some time it's not able to recover from those outages. Okay. So coming to the evaluation with respect to delay and packet loss. So here we inject delay between proxy and then the router, and also loss at the last hop, basically the link between base station and the user. So we see that the throughput is fairly stable and remains kind of same stable with our protocol, because there is no feedback loop. And any packet loss, it's recovered locally, and our protocol, it sits right on top of the bottleneck link. But with the ITCP, considering cubic, new and no, even with the small percentage of loss, let's say 0.1%, the throughput drops drastically. Okay.
You said there's a packet loss is recovered locally.
Yeah.
There is still a protocol keeping track of packet sequences, and you miss something, you ask for it again.
But TCP, like you have the loss mechanism, right? If there is any loss, you reduce the window. Yeah, backs off. But we don't have that. We use selective acknowledgement to again retrieve the lost packet.
So you basically have a different protocol over that interface where you don't have any backup window. If you don't have something, you just request again.
Yeah. It's like if there's any loss, like we request from the proxy, like you send me these packets, and the proxy will send.
So you gain because the proxy is very close.
Yeah, proxy is placed very close to you.
Not just that. I guess it's a short round trip time, but you're not designing it for multi-users or multi-links. It's a different protocol. You're not using TCP in the final.
Yeah, exactly. The TCP is only used from the remote file server, like several RTTs, to the proxy. But between the proxy and the UV, we have a pull protocol. Again, this proxy can be at the base station itself. Like
maybe his question, if your question is how will it scale?
Yeah, TCP protocol was created for a particular reason, and then it becomes ubiquitous. It's there in every device.
That's true, but TCP over mmWave is an ongoing work.
Oh, understood. It has its problems.
Right.
But you'll have to answer the question as to now the UVs will all have a different protocol, and it has to know it is working in this environment, so it will not use, the driver will not try to use TCP. It will do some other magic.
But again, in our case, like we have implemented this over UDP. So again, with just a push update, like you can update the UV stack, you can also update the base.
You are using UDP.
Yeah. Still standardized, but.
So that's out of scope as to how does the application decide or to handle this. So for example, if you take the 4K streaming example, maybe you use TCP to the server to set the session up, and then it says now I'm in the special stream mode, so I'm not using TCP, or even if it's TCP, it will come up with the proxy, and then I'm going to
Exactly.
Means you're assuming that it's a system which uses this protocol, and so we'll be aware the proxy exists, and then we'll switch to that special.
Exactly. Because we have a resolution server which does this mapping. You ask for content, and then you receive for the proxy address. So if the content is present at the proxy, you can retrieve using pull. You don't need TCP, because if your content is present close by, let's say round trip is 20 milliseconds, you don't require TCP in that case. You can directly use our protocol. But if your content is present remotely, like remote distant, which is let's say hundreds of milliseconds, then the TCP comes into play, where or other AIMD mechanisms which can retrieve the data packet from the remote file server to the proxy. Then from the proxy, our protocol kicks in. Okay, so yeah, next we have also evaluated our protocol on Orbit or Cosmos testbed. So here we implemented our protocol using click modular router. So here we have a file server, base station, and then the UV device. So in the case of click, each of those blocks, they're basically the element. So here we develop a trace-driven scheduler. We also have a pull buffer, pull logic again to pull the packet from the file server. Also, please note that in this particular evaluation or in this particular implementation, the loss is again recovered on a hop by hop basis. Like basically the reliability between the nodes are ensured in hop by hop manner. We used the millimeter wave trace, the following millimeter wave trace as cited as given in this paper, where you have frequent fluctuations between 4G and 5G, and also we consider Shannon throughput, like LTE we consider it as 10 megahertz and millimeter wave as 150 megahertz. So here I have a table representing file transfer size in gigabyte over multiple round trip times. So we see that with our protocol, a performance gain of 17.2x and 5.7x is observed with mmCPTP as compared to new Reno and Cubic, considering RTT as 50 milliseconds. We also have evaluated with respect to high speed, EA, BBR. Again, BBR is a recently proposed protocol by Google. It's a model-based protocol where at first you measure the bandwidth and then the round trip time and then you send the data. But again, we see that our protocol, it kind of performs better as compared to existing TCP schemes. And also we are close to the theoretical limit, which is again, like if you take the CDF of this particular graph, it's around 13.27. So we are operating closely at theoretical limit here. Yeah, this actually concludes my talk. I have 2 more slides to complete. So can I go ahead with that? Yes. Oh, okay. Yeah. So finally, to conclude, to solve physical layer challenges, we propose a spectrum consumption model assisted dynamic spectrum access, where specifically we propose spectrum management architecture, algorithm, access method, as well as experimentation framework on Cosmos testbed. To solve the network layer challenge, we propose a network-assisted distributed mobility management schemes. Specifically, we propose hard handoff with rebinding and soft handoff with multihoming, which again provides a seamless data transfer with increase in throughput. Again, to solve the transport layer challenges, we again propose a cross-layer pull protocol, again operating or specifically for millimeter wave network, where our protocol is capable of rapidly adapting to fluctuations in the MAC layer throughput, mainly to overcome the limitations of TCP. So as a next step is to evaluate the performance of our proposed the handoff schemes or the transport schemes or the spectrum management schemes with real 5G system, and also applying the machine learning techniques to enhance spectrum efficiency as well as the millimeter wave performance. Yeah, so this concludes my talk. I have a slide on acknowledgement. I think I can go. Okay. Yeah. So at first, I would like to thank my advisor, Professor Deepankar Rai Chaudhary, for all the help in carrying out this work. So I still remember our days where we used to discuss on new research topics, as well as writing papers, presentations. So thank you so much, Professor. Also, I'd like to thank my committee members, Professor Narayan Mandayam, Professor Predrag Spasojevic, and Professor Carlos and Professor Roy Yates, Professor Richard Martin, who were a part of my qualifiers and proposal committee meeting, for all the help. At each and every step, they provided me with the valuable feedback so that I can improve my work, and that actually helped me a lot so that I could reach this particular stage. Also, I would like to thank Ivan Seskar, because my work, it had some level of implementation as well as the simulation. So Ivan was my point of contact for the implementation. It may be with the accessing the nodes or collecting the measurements or even the spectrum topic. We discussed a lot on this, and again, thank you so much, Ivan, for all the help. Also, I'd like to thank my collaborators, Professor Gill from Columbia, again, Professor Carlos from Syracuse University, Ivan, Igor, Dragoslav, for our endless discussion on the spectrum topic. It has been a great collaboration, I think, for the past 2.5 years. I learned a lot on SCM standards, compatibility computations, and also the measurement campaign which we used to perform. Also, special thanks to Jiachan as well as Sumit for helping me a lot in my initial days, right from identifying or writing the research proposal, and also debugging the simulation, running experiments. So thank you so much, Sumit and Jiachan. I learned a lot from you guys. And also special thanks to the staff members at WinLab, EC, as well as Rutgers Global for all the help with the documentation, travel reimbursement, and like any assistance with the documents. Also, thanks to my friends at Rutgers and also my family back in India for all the love, care, motivation, so that I could complete this work. And also thanks to the National Science Foundation, specifically the Cosmos, Cosmic, and NRDC grant for supporting this work. So thank you so much for all the help and support. And these are all the list of publications which I have again obtained or which I've got throughout the PhD program. And yeah, so here these are all some of the experiences which I have again obtained throughout the program. I'd like to also thank my mentors at Qualcomm and InterDigital for all the help, for also providing me with the internship opportunities to work under them. So thank you so much. Also, thanks to the editors of the journal as well as the TPC co-chair for again providing me an opportunity to review some of the work. So thank you so much. That concludes my talk, and I would be happy to take any questions.